Hello everyone, my name is Wenxin Ding from Renmin University, and this work is initiated actually here at Kavli Institute of Theoretical Sciences, and it's done in collaboration with Rongyu. And thanks for the organizers for me to give me this chance to present this work. We're talking about the dynamical T/U expansion of a doped Hubbard model. So here's the brief outline of this talk. And first, the motivation, of course, is the high DC superconductors are long thought as a doped anti-ferromagnetic Mott insulators, which is believed to be described by a doped single-band Hubbard model with a large U. So it has been a 30 or 40 years old problem, but there have been many efforts on this problem for sure. But I would like to elaborate a few of the analytical perturbation efforts for this problem. And of course, the first is the famous TJ model that was first proposed by Fu Chun, my advisor at KITS, and which can be formally achieved through a so-called Schrieffer-Wolff transformation, which is that you can write a new set of fermionic operators then you apply this transform. You can, but at the end of the day, you get a TJ model, but the price you pay is that first the operator transformation is non-local, so the new fermions are not identical to the original physical fermions, and there are also additional, actually is also of the same order, t squared over u, terms are thrown away uncontrollably. And also there has been some efforts on the canonical perturbation theory in powers of u, but that naturally faces the issue of convergence, and it has recently been found that there's a incurable divergence or non-analyticity in the vortex function that even appears at the level of single site problem, and which is presented in this recent work, which I think is very nice. And personally, I think the more natural way is the strong coupling perturbation theory in terms of, say, the Green's function dynamically. But previous efforts of mostly they succeeded in some of the mostly half filling, but they all failed for doped case at low temperatures. Like for example, I think these are the two works that is very noticeable. They have done a very good job at half filling, but when they try to go to doped finite temperature series, they face a set of issues like convergence and also negative spectral weight, which presumably might be related to the negative sign problem, and also the widely used slave boson type of series that typically can only be solved at mean field level, and the dynamics are typically difficult to solve or generally ignored. So, first I want to point out what's mostly established for this field is that, and what a good dynamical theory should be able to describe, at least. The first thing, of course, is the single particle level. We should have something on this left panel where it's a schematic local density of states for the electrons. That when U is large, the electron spectral function should generally be divided into a lower Hubbard band and the upper Hubbard band. And when you dope it, not only the band gets a new pulse at the Fermi energy, and there are also spectral weights inside the Mott gap, and also there's spectral weights that gets transferring between these bands, which is sometimes called Mottness, that is calling this spectral weight transfer, which is also very difficult to generally to describe or understood analytically. And there are even finer structures as revealed, and also this picture is mostly established by the DMFT calculation. And there's also even finer structures showing that when you dope it, there's also a minor fraction of spectral weight transferring from upper Hubbard band to the in-gap states. And on top of these single particle properties, there should also be fluctuation effects, which namely is mostly the spin-spin interactions. We know that at half-filling, we should have the anti-ferromagnetic superexchange interactions. But even that is not simple, because when you dope it, it is long known that if you work with TGM model and trying to describe real materials, you have to go with the Gutzwiller approximation, which is basically you have to renormalize the T and the J phenomenologically with a factor that dependent on doping. And theoretically, there has been the famous Nagaoka theorem, which is basically saying if you set U to infinite and you add one hole to a finite system, the ground state of a system pool just directly turns completely ferromagnetic. And ever since then, there has been a long history of controversy about whether this ferromagnetic phase could survive in the thermodynamic finite doping and even finite U. And more interesting is that recent experiment has also brought these purely theoretical questions into reality. There has been some ferromagnetic fluctuations that have been observed in the overly hole-doped cuprates, and even recently there has been reported a static ferromagnetic phase is observed in the overly electron-doped cuprate. And of course, I guess everybody also heard of in this magic angle twisted bilayer graphene, the superconducting phase is found to be ferromagnetic. And this would be mostly the aspects I want, or I try to convince you that today that I achieved, my theory at this stage is able to at least to capture to some extent all these features of the single band Hubbard model. So I want to comment back to the pure theoretical perspective is that all these strongly coupling problems share a common difficulty, which I would call it the non-canonicity, which basically is saying that if you are dealing with bosons, the operators you use to construct the problem has a commutator that is not simply proportional to a delta function. And if you are dealing with fermions, the anti-commutator is not a simple delta function. The consequence is severe. You will have no weak theorem. So all the Feynman diagram approach just simply breaks down. And here's a few examples. Like in TGM model, this operator, so-called the Hubbard operator, is nothing but the Gutzwiller projected fermion operators. That is anti-commutator. Aside from this delta function, it has a dynamical correction that is proportional to a spin operator, a spin flipping operator. And in Hubbard operators, you also have to include these Hubbard operators involving double occupancy. And also, if you're dealing with quantum spin systems, it's mostly a boson, but its commutator is still proportional to the local SZ operator. And also locally, it has another aspect. It behaves like a fermion if you look at the one site. So, and to deal with this such non-canonicality, I want to actually there is an ancient controllable way to go around, which is the Schwinger's many-body theory approach, which is basically you start from the Heisenberg equation of motion for operators, and you convert it to a Schwinger equation of motion for the Green's functions. And this approach has been recently pioneered by Shuren Shastri and applied to the TGM model, in which it was able to solve for the dynamical properties of TGM model to get a first microscopic theory for a strange metal phase out of TGM model. And there has been some, back in the 60s, there's some efforts on the quantum spin problems that actually I would rediscover and use in the next part of the work. And of course, there are some improvements that I would like to that I personally add to the work. So with this algebraic perspective in mind, we actually look at the Hubbard model in a different way. We look at its algebras, and we realize that locally, if you look at the commutation relations of the fermion operators along including this density operator, you can actually identify this part, this density operator, subtract 1/2. You can identify that as some sort of spin SZ operator, and then they would satisfy the spin, the usual SU2 spin algebras almost. There's a difference in the Casimir, so-called Casimir elements. For this spin 1/2 problem, it's just a normalization factor. And then, this is, please note, this is for one species. So, and if you look at the both species of fermions, then you would also have the spin SU2 rotation algebra, but the Hubbard U-turn is naturally spin rotation invariant. So, which means that if you rotate the physical spin index by some matrix, you can still define this charge raising or lowering operators that satisfy this SU2 charge algebra. So, with this in mind, we revisited some of the so-called slave spin representation for the Hubbard operator, which previous construction just saying it's diagonal in the spin index. So with this algebraic perspective, we realize that the charge algebra and the spin algebra should be separate and independent. So the natural way is to introduce to define it in this way, where the slave spin and the physical spin or the spinons have independent indexes. And so then what follows is just similar to the previous construction. The Hubbard U-turn becomes SZ, the Ising interaction, and the chemical potential along with the constraint just becomes a longitudinal field, and the Hubbard turn just becomes slave spin and the spinon vortex. And here's I also want to emphasize here the interpretation should be the following. The F spinons introduced here should be really considered as some auxiliary fields representing this spin flip degrees of freedom that we wrote down previously here, and also because we are treating the slave spin here as bosons, so we use this F spinons to also carry the fermionic statistics. And then the slave spins are what's responsible for the charge excitations, and it should be responsible for the large energy pole structures for the local density of states or the spectral functions. So next, because to solving the problem in general, of course, is very difficult. We start from what has been done, a static mean field treatment of this slave spin representation, which has been used extensively in many works which was able to capture many of the, like in iron pnictides, and many of the important physics in those real systems. But here we're just looking at a simple single band Hubbard model. So basically you just decouple this Hubbard turn in a mean field fashion, and introduces two mean field parameters. So the slave spin Hamiltonian just have just the XY type of interactions, and this free spinons, for the spinons, this Hubbard turn just becomes just a Hubbard turn. And even for this XY model, it's still difficult in general to solve. And we do another mean field approximation so eventually we transform the atomic limit into an Ising model with a longitudinal field and with a transverse field. And this transverse field is just a self-consistent mean field parameter. And then we assume a 2D square lattice with only nearest neighbor, and this is a parameter setting. And here's a brief review of the mean field result, which is nothing but a standard Brinkmann-Rice type of Mott transition driven by doping or chemical potential. And so you can see clearly that Z, which is the square of the transverse magnetization, is linear in doping. And of course, as a promise, as a title promises, a dynamical mean field theory by hand. So what's our focus will still be the dynamics or the dynamical structures of the physical electrons Green's function. So in general, normally this physical electrons Green function can be written as a product, approximately as a product of the slave spin Green's function and the spinon Green's function in real time and real space. And then you can transform it to Fourier transform, and you can express the physical spectral function as a convolution of the two spectral functions. And typically, the mean field parameter is such that the spinon bandwidth is much smaller than that of the slave spins. So this rho f spinon spectral function in this convolution mostly behaves as a delta function. It just broadens the slave spin spectral function a little bit. And so we can approximately write that the physical spectral function is almost identical as the spinon of the slave spin spectral function. And then the final question boils down to how can we solve this slave spin Green's function or spectral functions for this transverse field IC model with good analytical properties. This means that it should have this spectral sum rule and all that. So as I introduced, so we should take this stringless approach. We first look at the equation of motion for the operators, then convert that into the equation of motion for the Green's function. And of course, all the difficulties is in this vortex function. And luckily that in the IC limit, you can simply factorize this SZ out exactly. So this is an exact identity for the IC limit, and we can write down the Green's function rigorously. And half filling, we can set these parameters to be such so that you can clearly see that one branch of the slave spin have a pose at minus u at the u half of u, and the other branch has a pose at the minus u half. And together, it just gives you the standard upper and the lower Hubbard band. And this also agrees with previous like straight rotor theory and many other perturbation theory and other slave particle type of construction, if they capture dynamics. So, but with the hopping turning on, or the transverse field turning on, there are some very non-trivial effects. First is renormalizing the ground state wave function. As even if we have an infinitesimal transverse field, the slave spin ground state which initially has a twofold degeneracy, now the degeneracy is immediately lifted. And also, the ground state would develop a transverse magnetization, and also the total magnetization would also vary, so which would be our doping. So, but the normalization of the wave function can be computed either through diagonalization, or we can compute it also through the Green's function method. And these two approaches generally agrees. And the most important part, of course, is the correction to the Green's function, or to the equation of motion. So we have to, here's how we can, first we need to construct the Green's function with just the Ising term of the Hamiltonian, but with the arbitrary state. So luckily, we can still do that by just construct it as a superposition of all these Green's function for these different good states. And we can still have a rigorous Green's function without the transverse field Hamiltonian term. Then we should impose the changes on the equation of motion and apply it to this unperturbed Green's function. And what's different is that now we see that we have a term that's proportional to the transverse magnetization, and also here, sorry. And also the vortex function in general becomes very difficult to solve, but we're interested mostly in the effects of the transverse field. So there's a term that's still proportional to the transfer magnetization in the vortex function as well. So this is the important part. And there are some other the more dynamical parts that are not included. So with these previous approximations, now we can try to compute the Green's function perturbatively in the transverse field, Hx. So in general, we can, here's the expression that for the perturbative term that here we can already see later what we will see in the plots is that it has new poles at the plus H, and it has also a zero frequency pole. I would emphasize that it's a dynamical zero frequency pole that we will see later. But even though this first order perturbation theory still has some issues that you have to do RPA approximation on top of that. Otherwise, you will see we will get some similar negative spectral weight problems as in previous other perturbative calculations. Oops. And okay, and so now with this is and in the end, this is the result I will show with the perturbative result with additional RPA approximation. And this is the left-hand side is the local density of states we get at different dopings. And you can see it has the lower Hubbard band, upper Hubbard band, unsurprisingly. And we also have the in-gap state, which is stepping from the plus H pose. And you also get a pose at the Fermi energy, which is the correspond to the quasi-particles. And this is and I also plot the spectral weights with labels corresponding here, W1, W2, W3, W4, how they evolves. And the dashed lines are asymptotic fittings. And the fitting results is, I would say, let me see, the fitting result is here. So I would like to point out is that this is really comparable to, qualitatively comparable to these DMFT calculations that for these spectral weight distributions. And so this is some, in details, as I mentioned, these are the 4 poles approximately. And the spectral weight, this is the lower Hubbard band. You go with that picture. And we also get, and we also have the right upper Hubbard band and the middle and the in-gap states, which we actually identify a so-called double on density, which is the spectral wave transferring from the upper Hubbard band to the in-gap states, as we have it as approximately 2 twice delta, which presumably is coefficient actually should involve with U. And this is what in the CDMFT calculation, presumably, it just read off by the eye. But I think the qualitative agreement is there. And what I want to emphasize, a more important aspect actually, this zero frequency pole, this dynamical zero frequency pole is actually proportional to delta function derivative, which when you plug into the convolution formula, it actually gives you a correction to a contribution to the physical electron spectral function, a term that is proportional to the partial omega of rho f. If you interpret this rho f as a conventional fermion spectral function, then which is even in omega, then you get a term, a contribution that is you typically call the so-called dynamical particle asymmetric term near the Fermi energy, which means that you have in the self energy you have terms proportional to all the parts in omega, like omega to the cube, which has been found previously in the ECFL calculation and also in the DMFT calculations. And I want to emphasize this is generic behavior, not the mean field artifacts, because even if we try to solve the real beyond the theory beyond the mean field approximation like the XY model, you will still get when you polarize the state, you will still get a spontaneous magnetization in the transverse direction, which will still give you this type of pose, and that's this type of contribution to the physical electron grid function. And next is we will try to do a formal dynamical theory expansion using a Lagrangian series of the Hubbard model, which is in general, we can only say that formally we can do this. So, and the strategy is that you just treat the slave spin as some conventional bosons, and you can do the cumulative expansions log determinant, and you can get some effective Lagrangians, and you would, in any, you have to require self-consistency between these two effective Lagrangians of spinons and slave spins. And you can recover the mean field theory, of course, at the lowest order. And the benefit you get is that you can now consider fluctuations at the second order from expanding from this cumulative expansion. And for the most important term, of course, is superexchange term, or the spin-spin interaction term, which is nothing but a bubble diagram from this expansion. And we can get the leading term, which will be correctly recovered as a proportional t-square over u. There's a factor of 2 missing that we also previously know how to recover this, but we'll not go to the detail. And most importantly is that with the onset of, with the finite doping, we actually get the additional terms, which is the J1 here. And because we are doing an analytical theory, so we can get a asymptotic expansion in powers of delta and mx or z. That first we get that the J0 term, the antiferromagnetic superexchange term, gets a correction proportional to 1 minus 2 delta. And this J1 term actually turns out to be ferromagnetic. And it's proportional to delta and z, but it has no dependence on u, which means presumably that this term can survive in the infinite u limit. So this links this ferromagnetic interaction possibly with the Nagaoka theorem. And this is a numeric calculation of the j's that this is the overall j with the j0 plus j1. And this is the j1 term that shifted in order to make the plots easier to see. That you can see the trend is almost identical with what we presented as the asymptotic formula. And so in the end, to point out that with this theory, we can now should be able to write down a set of low energy effective theory for the Hubbard model, which composed of 2 pieces. The first piece is still the slave spin part, which is described as charge excitations, which is Ising term plus the transverse, the xy term, that is the strength of which is determined by the slave spin part. The F fermion, the spinon part, and there's also the spinon part, which describes the magnetic interactions, and which we will have the J0 term, which is the TJ type model, but now we acquired a Gutzwiller approximation type of renormalization factors. And there's also this J1 term, which is a ferromagnetic term. And this is the slave spin effective interactions. And but still, then it will always be the slave spin part to dominate the electron dynamical properties. And here's the summary. So we have in this theory we have developed a new representation, slave spin representation, by our algebraic consideration, and which enables us to capture the correct local pole structures and the corresponding spectral weight distributions, largely in qualitative agreement with the MFT calculations, and like also actually with the ECFL theory. And we also recover the DJ model with the Gutzwiller approximation from just considering the fluctuation effect due to doping. And on top of it, we found a ferromagnetic spin-spin interaction channel in the dope regime. So this so in the future, we want to consider whether the relevance of these ferromagnetic fluctuations, whether it's relevant to ferromagnetic fluctuations observed in the whole doped cuprate or in the ferromagnetic phase in the electron overdoped cuprate, and whether that relation to Nagaoka theory is real, or is it Oops, sorry. So, but I think that's most of it. And
okay,
thank you.
So